We're now going to talk about the Newton-Raphson method. This method can be used in order to find roots of equations, but in some sense, we can consider it a further improvement of estimates that one can get using linear approximation. Because as we're going to see, the whole method is based on linear approximations, at least indirectly. So let's see what we have here. So imagine that we have a function, and for example, by using the intermediate value theorem, we know that this function has a point where it's equal to 0. So let's say this is the point. So let's call this function y is equal to, y is equal to f of x. And we would like to know what this point is that is equal to 0. So here's what we do. We cannot directly find this point. It's not a matter of guessing or a matter of some simple method. So what we do is we start with a first guess, where let's say that this is our first guess. And nobody really expects that just by our first guess, we're going to find that point. But here's what we do. We consider the tangent. So let's call this first guess, let's call it x naught. We consider the tangent to the graph at that point, and we ask, where is the tangent? Where would the tangent intersect the x-axis? And we find where the tangent would intersect the x-axis, and that's our second guess. So this would be x1. Okay, as you can see from this picture, it brings us a little closer to the point that we want to find. And then we continue like this, meaning we find the tangent at the new point that we got. And we ask, where does that tangent intersect the x-axis? And that will be our point x2. And as you can see even from the picture, this method is going to bring us closer and closer to the point under question. So it's actually a brilliant method. And as we're going to see numerically, it can give us some quite strong results. So let's take a look at an example. Before we get to our example, let's find our formula. So let's start with the first step. So what is the equation of that tangent that we got up here? So the tangent at the point x naught will be y minus f of x naught is equal to f prime at x naught times x minus x naught. And to find the point x1, we need to find where this intersects the x-axis. And a point that belongs to x-axis has y-coordinate equal to 0. In fact, y equals 0 is the equation of the x-axis. So if in the above equation, the equation of the tangent, we set y equal to 0 and try to solve for x, isolate x in order to see where it intersects the x-axis, here's what we're going to get. So minus f of x naught is equal to f prime at x naught times x minus x naught. And we're going to get, assuming that the derivative is non-zero, which is a pretty mild assumption. Usually we can check that assumption in the vicinity of a point where of a root that we're trying to locate will be x minus x naught, and eventually we get that x is equal to x naught minus f of x naught over f prime at x naught. And this is what we called x1. So x1 is x naught minus f of x naught over f prime of x naught. And The nice thing is that if we ask now, so what is x2, we don't have to do the whole work from the beginning. In other words, what will happen is x1 now will play the role of x0, and x2 will be x1. So x2 will be equal to x1 minus f of x0 over f prime of x0. And this formula holds pretty much for every step. So in other words, the Newton-Raphson method can be described as follows. We wish to find the root of the equation f of x equals 0. Actually, here, saying the root is something that needs to be clarified, because you may have a function that has more than one root, meaning its graph intersects the x-axis at more than one point. If you start with a random first point, then usually what will happen is your method will approach one of the roots. If you wish to find all the roots this way, you have to be careful how to choose the first point. And this is where somehow knowing the monotonicity of the function, having applied the intermediate value theorem can give you, and even knowing the concavity of the function can give you some information about where to begin if you want to target a specific point. In the examples that we're going to see, we will be interested mostly in one root, and it will be straightforward that our method is going to converge to that root. But in general, one has to do a very careful study before applying this method, because you might get a different root than the one that you initially wanted. In any case, we begin with a first, allow me to call it guess, x0, and we use the formula. So now, instead of writing the formula for x1 and then for x2, I'm going to write it in general. Xn plus 1 is equal to xn minus f of xn over f prime of xn. So this formula will be true for n equals 0, 1, 2, and so on. Okay, so if you set n equals 0, that gives you x1. If you set n equals 1, that gives you x2, and so on, and so on. So I think it's time to apply it. And let's take a look at the first example. Now, remember that I said that one can consider this as a vast improvement on what we did before in order to approximate roots. So imagine that we wanted to find the square root of 2. With the approximation method that we described in terms of the linear approximation of the function, you might get a first guess, but this guess is going to be pretty weak. And also, it cannot be improved. With the Newton-Raphson method, you can improve it and come as close to the root as you like. And let's see how this is done. So the first thing is, we don't know, I mean, we need a function, right? So we need to ask ourselves, what is a function that has square root of 2 as the root? So here we can play a very simple game. You know, if x, which we don't know exactly what it is numerically, is square root of 2, then x squared is equal to 2. So we try to actually express it as a root of an equation that doesn't use any direct reference to the number itself, meaning to the number square root of 2. And so when we start with x is equal to 2, and we square, immediately the square root of 2 disappears and we have 2 instead, and we can have x squared minus 2 is equal to 0. So for that reason, we define f of x to be x squared minus 2. And we know that if we apply the Newton-Raphson method, we should approach a root of this equation. Now, here's where things become interesting, but you will see at the same time they're not really problematic. I mean, you can already predict what this graph will look like. It's a parabola, right? So it looks like this. So it intersects really at 2 points, at square root of 2 and at negative square root of 2. Okay, if you take any initial point x naught, which belongs to the positive part of the x-axis. So if you start here, certainly that will continue, and you can see from the pictures that it's going to take you closer and closer to the square root of 2. But if you start by the same token with some number on the negative side, that is going to be attracted by negative square root of 2. So for example, in this case, you should not take x naught to be on the negative side if you want to specifically approximate square root of 2. If you want your method to eventually lead you to square root of 2. But as we said, let's take a first case. So let's take x naught equals 1. And here's the idea. Instead of applying the formula numerically every single time, we're going to try to find a general expression for the next step. So we know from the formula that we gave that xn plus 1 is equal to xn minus f of xn over f prime of xn. Okay, so let's work it out for the specific function. This will be xn minus xn squared minus 2 over, and the derivative of x squared minus 2 is 2x, so this will be 2xn. Okay, and now let's try to simplify this, make it a little nicer. Minus xn over 2 plus 1 over xn, and this is xn over 2 plus 1 over xn. And here it's quite traditional to actually write this as, we can leave it like this first of all, but it's easier to write it, it's traditional to write it as 1/2 xn. Now be careful, you can put here 1 over xn, because when you multiply by 1/2 you will have this unwanted 2 on the denominator, so it's going to be 2 over xn. And if you multiply out, if you FOIL it, you will see that what we just did is absolutely correct. So in other words, we obtain the formula xn plus 1 is equal to 1/2 xn plus 2 over xn. And this will be the formula that we will use along with the initial choice x naught equals 1 in order to approximate the square root of 2. Okay, so what is our x1 then? x1 will be, now I have to go to this formula, and wherever I have xn, I'm going to plug in x naught, meaning x1. So it will be 1 plus 2 over 1, which is 3/2. Okay, so the next step that we find is 3/2. Okay, it actually might be a good idea to use a calculator to know what we're heading for. So look, if you use a calculator, you will get that, and I will put that right here on the top that square root of 2 is known to be 1.414213562. And right now we started with x naught equals 1, and we have x1 equals 3/2, which is 1.5, right? I mean, 1.5 is not that bad, but it's certainly not impressive if the number is really 1.41421. And I promised you that this method right here would be rather impressive. So let's continue then. Let's take one more step. So x2. Let's write it 1 so that you can see it. It will be 1/2 x1 plus 2 over x1. And what is our x1 this time? It's equal to 3/2. So this is going to be 1 over 2 times 3/2 plus 2 over 3/2 on the denominator, which is equal to 1/2 3/2 plus 4/3. Okay, so let's clear denominators in the parentheses. So we will have 9 plus 8 over the common denominator 6. I just cross multiply and we have the 1/2 right in front. And that will give us 17 over 12. So our second guess for, or if you like, our third guess, given that the very first guess was 1, is 17 over 12. Okay, I mean, we can ask now, is 17 over 12 any better? Allow me to use quickly a calculator in order to get it as, that's 1.41, and then you have a string of 6s that keeps going. Okay, I mean, it's not too bad. We already guessed 2 decimal points, right? Why don't we take a deep breath and take one more step? Okay, so let's find x3 now. So x3 is going to be 1/2 x2 plus 2 over x2. And you know what? I would like to stop exactly where we cannot do the computations from memory anymore. I mean, if I have to do it using a calculator, if I have a calculator, then I hit square root of 2 and that's the end of the story. I'm saying, let's say that you're lost on a deserted island and your life depends on knowing what square root of 2 is. Okay, very unlikely scenario, I'll give you that. But let's say that you are in such a situation and you would like to compute it, and certainly you don't have a calculator. So let's see how close this method will take you after this step. So we will have 1/2, and then it's x2, which is 17 over 12, plus 2 over 17 over 12, which is going to be 1/2 17 over 12 plus 24 over 17. Okay. And now we need to cross multiply in order to consider the correct denominator. So how much is 17 squared? It's 289, right? 289. It's, if you think about it, it's 10 plus 7 all square, so it's 10 square, which is 100, 7 square, which is 49, and their double product, which is 140. So it's 289 over the common denominator, which will be what? So you have 12 times 17. 10 times 17 is 170. 2 times 17 is 34. 170 plus 34, that's 204. Like I told you, let's stick to computations that we can do from memory one way or another. And what is this going to be? Then you have to multiply 12 times 24. 24 is 2 times 12. 12 times 12 is 144. And 2 times 144 is 288, right? Just one number below that, over 204. And that is going to give you what? Well, let's play a little. If you had 300, so we want to add 289 plus 288. If you were adding 300, you would get 600. By how much smaller is this? So on the one hand, you're missing 11. On the other hand, you're missing 12. Overall, you're missing 23. So 600 minus 23 will be 577 over, so I have 204, and I also have my denominator, which will make it 408. Okay, so 577 over 408. And let's use a calculator. Again, you could do this division even in the scenario of our deserted island, but you know, then again, it will take a little more time. And now we can see that the decimal that we get from this operation is ready. It's 1.414215686, and it continues. So now it's reckoning time, right? Let's take a good look. What do we have here? How many decimal points have we achieved? 5 decimal points with just 3 steps, because we started with X naught and we had to do 3 computations that, as you saw, they're not entirely difficult. They are possible. And we got already 5 decimals. That's actually very, very impressive. And one question that arises here is, when exactly do you stop? Because you can keep going. Let's say that you're very patient and you start doing computations with big numbers. You can see that here the denominators are going to explode, and the computations are going to get much more challenging. So I certainly stop right here. But the question is, when exactly are you going to stop here? And the answer is, as you compute these approximations, you will see decimal points stabilizing. So you see, if you compare this 1.41666 with the next one that we found, 1.41421, and so on, you can already see that 1.41 is common in both of these. And that's exactly the pattern that you're going to notice. In other words, you're going to see your decimal expansions stabilizing, at least in their leading parts, in their parts in the beginning. And as you get more and more decimals that stabilize, you will decide for yourself when exactly you want to stop. If you want 5 decimals, fine. If you want 10 decimals. So here, after I took this step, all I can say for sure, or I can be pretty sure, is that it's 1.41. If I want to be more certain that it's I have more, I wouldn't know it without having the formula for square root of 2, without knowing what square root of 2, which of course I did here. So I would have had to take one more step, and then I would realize that 5 digits have actually stabilized, and so the process can end there. Or you could take it further if you wanted, let's say, 10 decimals and so on. And please try to understand that this method was devised in an era that people did not have any electronic machines. They didn't even have electricity, right? They didn't even know how to use electricity. So there were some mechanical calculating devices like the abacus that were available, but pretty much people were on their own. Obviously, they had more time than we have nowadays. Regardless, this gives us a very strong method that allows us to make such computations. Please understand that in general, the method that you should know here, the formula that everybody should remember here is this one. This is the important formula to know, this one. This formula that we gave right here was specific to the problem of computing the square root. That's why I would like to do one more example, a much more trivial example, by using a different function. And let's see. So I would say take two steps with the Newton-Raphson method. In order to approximate the root of the equation x cubed plus x plus 1 is equal to 0. This is an interesting equation. The derivative of the function f of x equals x cubed plus x plus 1 is always positive, so that the expression that you have on the left is a strictly increasing function. And it has exactly one root because the limit as x tends to negative infinity is negative infinity, and the limit as x tends to positive infinity is positive infinity. That tells you that this function has both negative and positive outputs, and thus it will also have the output 0 by the intermediate value theorem. Here, different people would start with different numbers. So start with x naught is equal to 0. As I said before, I mean, don't expect any miraculous result with two steps. I just want to give one more example of how to set up the Newton-Raphson method. So, so here's what we need to do. So, let's first of all define f of x to be x cubed plus x plus 1. We clearly need a function in order to be able to get started with our method, right? So the formula now will be slightly different than it was before, but we can still find the general formula. So we can write that xn plus 1 is going to be xn minus f of xn over f prime of xn. And one more step, xn minus xn cubed plus xn plus 1 over 3xn squared plus 1. Okay, I'm not going to try to simplify it. I mean, you know, I could I could try to clear denominators and so on, but I will not attempt to do something like that, even though it might give something pretty nice. At think actually it will give something pretty nice. But, let's stick to this and let's start with x naught is equal to 0. Then by the formula that we just produced, x1 will be 0 minus, on the top you will get 1, and on the bottom you will get 0. So your first approximation is -1. By the way, if you didn't already notice it, please note that this equation, there's no way it can have a positive root, right? Any positive number you plug it in will give you something positive on the left. So the fact that we find -1 makes complete sense. And now let's take one more step. Okay, so what is x2? x2 will be x1 minus x1 to the third power plus x1 plus 1. I'm writing it now. Before I didn't write. Maybe I was very happy that I was dealing with 0 and it was a very simple computation. But here, let's write it down. So it will be -1 minus, and let's see what we get here. So on the top you have -1 cubed is -1. Another -1 will give you -2 plus 1, that's -1 on the top. And the bottom is 4. Okay, so it's pretty much -1 plus 1/4, which will be -3/4. So that's the guess that we have with by taking just 2 steps. So our guess for the root is that it's -3/4. So we started with something very generic. We didn't even take into consideration that the root was negative with just 2 steps. And I'm curious here if an internet search can give me right away the root, which is somewhere between -1 and 0, but just in case to see how close we were. No, I didn't find it with simple search. But still, 3/4 in just 2 steps should be considered as satisfactory. Yeah, I see here that with 2 iterations of the Newton-Raphson method, if you start with 0, the second iteration would give us -0.68. I'll stick to the -3/4 because the problem just asked us to take 2 steps. And that's it. So in conclusion, one needs to remember just this formula. And one common mistake that I have seen here is people getting confused with the minus and the plus that we had in the case of the linear approximation. So in the case of a linear approximation, we had the plus. It was f of a plus f prime of a times x minus a. Here we have a minus. And I think that's something that one ought to remember. And that's all. Thanks for watching.